Hello everyone, since the AMC tests happened earlier this month, I figured I'd go over some solutions to the harder problems. In this video, we'll be going over the last 5 problems of the 12A. Let's get right into it. First up, we have problem 21, which gives us 3 randomly chosen distinct vertices P, Q, and R on a regular icosahedron and asks us to find the probability that the distance between Q and R is greater than the distance between R and S. The distance function is defined as the minimum number of edges one must traverse to connect the initial point to the endpoint. Firstly, notice how Q and S are arbitrarily chosen, so the probability that d of q, r is greater than d of r, s is equal to the probability that d of q, r is less than d of r, s. Due to this symmetry, we can say that the probability we are looking for is half the probability that d of q, r is not equal to d of r, s. Thus, it suffices to find the probability that d of q, r equals d of r, s, or the probability that q and s are equidistant from r. If we assume without loss of generality that r is this particular point on the icosahedron, then q and s are equidistant from r when they are both on the same layers as colored on the diagram. Thus, the number of possibilities for q and s to be equidistant from r is 5 times 4 plus 5 times 4. And the total number of possibilities for Q and S is 11 times 10. The probability of Q and S being equidistant is then 40 over 110, or 4 over 11. Taking the complement of this value and dividing by 2 gives us our answer, which is 7 over 22. Problem 22 asks us to evaluate f of 2023, where f is the unique function defined on the positive integers such that the following condition holds for all n. Generally, when dealing with mystery functional equations, there are two approaches. Identify the function as a well-known function like log or cosine, or test different values in order to figure out the function's behavior. In this case, it turns out that we should take the latter option and attempt to test different values. Let's start with n equals 1. Plugging this into our condition tells us that f of 1 is equal to 1. Since the condition's summation is taken over all the positive divisors of n, it makes sense that we should move on to trying numbers which are prime, since prime numbers only have 2 divisors. In particular, if we let n equal a prime p, then we can solve for f of p to find that f of p is equal to 1 minus p. We can also set n to p squared to find that f of p squared is also 1 minus p. However, realize that 2023's prime factorization contains 2 distinct primes, so we need to find a way to evaluate this function for the product of 2 primes, not just 1 prime. Okay, this is where some creativity might have to come into play, and this idea might only come up to you in a contest if you're already familiar with Dirichlet convolutions. Consider 2 primes, p and q, and let n sub 1 equal p to the m, and n sub 2 equals q to the n, where m and n are non-negative integers. Plugging in n equals n sub 1 and n equals n sub 2 gives us 2 conditions. If we multiply these 2 conditions together, we get the following, which actually turns out to be equivalent for the condition when n equals n sub 1 times n sub 2, as long as we assume that f is a multiplicative function. That is, f of x times f of y equals f of x times y, for a relatively prime x and y. Thus, if the condition is satisfied for all n which are a power of a single prime, and we just let f be a multiplicative function, then the condition is actually satisfied for all integers n. So, now that we know that f is multiplicative, we can easily find f of 2023. In particular, f of 2023 is equal to f of 7 times f of 17 squared, which is just 96. Problem 23 asks for the number of ordered pairs of positive real numbers a, b, satisfying the following equation. At first, this equation seems asymmetric, but if we substitute c for 2 times a and divide both sides by 2, we can create a very symmetric equation. In addition, c is positive if and only if a is positive, so we just need to find the number of ordered pairs c, b that satisfy our new equation. Now, our best bet to narrow down the number of ordered pairs that could be possible solutions is through inequalities. In this case, we can apply the AMGM inequality to 1 plus c, 1 plus b, and c plus b individually, which then tells us that the following inequality holds. Since our equation is the equality condition for the inequality, there's only one solution and we're done. Problem 24 asks us to find the ones digit of k, where k is the number of sequences of sets, such that the length of the sequence n is at most 10, and that each set in the sequence is a subset of the next set in the sequence, with the last set being a subset of the integers from 1 to 10. Firstly, notice that once a number begins appearing in an element of a sequence, it can't disappear, because each set is a subset of the next set. Thus, every sequence can simply be described in terms of the first appearances of each number from 1 to 10 in the sequence. For example, the number 1 can either not appear at all, appear first in the first set, appear first in the second set, or etc. Thus, for a particular n, each number from 1 to 10 has n plus 1 options for when it first appears, resulting in a total of n plus 1 to the 10 ways for a fixed n. Evaluating this formula for all n from 1 to 10 and calculating the sum modulo 10, we get that our answer is 5. Problem 25 asks us to find a sub 2023, where a sub 1, a sub 2, all the way up to a sub 2023 is the unique sequence of integers such that the following equation holds. The equation is obviously a trigonometric identity, and generally in trying to prove trigonometric identities, the easiest proofs come via usage of complex numbers. Let z be the complex number cosine of x plus sine of x times I. Notice that the tangent of 2023x is the same as the imaginary component of z to the 2023rd divided by the real component of z to the 2023rd. With this in mind, we evaluate z to the 2023rd power to get the following by the binomial theorem. Dividing the imaginary component by the real component, we get the following for the value of the tangent of 2023x. We can manipulate the sines and cosines into tangents by dividing the top and bottom of this huge fraction by cosine of x to the 2023rd power, giving us the following. Thus, our desired answer is -1. And that's it. Thanks for watching, and I'll see you guys in the next video.